Sí, porque te he dicho, no usamos de la montaña.
Sí,
para ver. Sí, en esta no he hecho en otra cosa que ya creo un poco de si se hacía al final es mejor porque
Okay, good afternoon everyone. Our speaker today is Jose Ramasco from ICI, which I never remember what it means, Institute for Scientific Interchange in Turin. Jose got his PhD in 1997 in the Instituto de Física de Cantabria in Santander. At the time he was working in Raffin phenomena, sun piles, organized criticality, that type of thing. After his PhD, he moved first to the Centro de Física de Porto, then to Atlanta in the USA, and then finally to the ICI in Torino, where he's today. He's been working in a number of different topics. He claims that his research interests are complex networks, inference and data mining, social activity and dynamics, epidemic spreading, non-equilibrium statistical physics. Lately, he's been doing a number of very interesting works on network theory, detection of communities, and so far. But that's what he's going to tell us about today. But he's also been very active lately in an important international project on the spreading and transmission of the new influenza, what we call here VPA, and he has a recent paper in a journal that, for those of us that didn't know, it's an important journal, which is BMC Medicine. On the title of that paper is Seasonal Transmission Potential and Activity Peaks of the New Influenza A, H1N1, a Monte Carlo likelihood analysis based on human mobility. I'm telling you because that's not what he's going to tell us about today. And if anyone wants to talk to him, he's here today and tomorrow. Thank you, Jose.
Thank you for the introduction. So yeah, it's true. There will be some things coming out soon about that part of my work. No? So essentially, is the case to forecast the evolution of pandemics or even seasonal influenza, depending on how you work on it. Still, again, I prefer here to talk about this work. This is one of the other things. This is related to structure in complex networks and inference of that structure, essentially when you have real networks at hand, no? And you want to know something about what is happening in there, or which is the phenomenon that is behind that structure. So this is essentially why I give this title to the talk is the statistical significance of communities in networks. I prepared a talk in a kind of introductory way, so thinking that it would be 50 minutes or 45 minutes. So probably for the people that already know something about networks, the first part will be so interesting, because I will try to show you what I understand by communities and why they are so interesting. And then I will go really to the problem of what means to have statistical significance in this kind of structures. So this I worked on with these two guys here also from the side. And there is a student also in Polytechnic, so this is why I have the two affiliations, but essentially we are all in the side affiliation. So this is the outline of the talk. I will tell you what communities are and what they are interested in, and why there are so many people working on that and trying to find these here methods to find them. The only problem about communities is that they are not well defined. So everybody is fighting to find them and to see where they are, but nobody knows exactly what they are exactly. And so this is the mathematical definition for the community. So everything is based in an almost hand-wavy definition, which is something that you have more connections inside than outside. But I will show you some examples about that. Then I will talk about what is this statistical significance and why it's so important. Define these two quantities that are probabilities and are, let's say, the cornerstone of the work. And then I will show you some results of C and D scores on benchmarks. So that means on networks that we have created to test these quantities, and also on real networks. And that will conclude the work. So, okay, why this thing of the communities are important? Okay, so here you have 4 exampple of networks. Well, in the internet, everybody knows about it, essentially. So every computer is connected among themselves, and that generates a huge thing with everything connected. Here, what we are seeing is just a photo not of the computers, but of the web pages. So the web pages also have interlinks, and that generate a homogeneous network with millions and millions, probably thousands of millions of nodes now. And every of them are connected with interlinks. Complex networks are also useful to represent other kind of systems. For instance, here you have proteins. Every node is a protein, and then there is a link every time that there is an interaction. Think that, and that means, as I said, you can represent many complex systems. Even, for instance, this is a social system. Here, every node represents a person, and relink is the interaction among the cells. I will talk about this particular network a little later. And of course, you can go to the economy where you have companies and economical relations between them, and there is a transfer of services, money, etc. So all this is to say that networks is a very useful to actually represent empirical data coming from very complex systems. This is essentially to make a zoom on one of these examples of what networks are useful to. Here you have the interaction network for proteins, and as you see, I mean, actually, these nodes are usually representing big structures. No? So you can have this kind of groups of aggregates, things inside of this node if you look at different scales. So essentially here, in this representation, you have one node per protein, but each protein has a complex structure, and then inside of it, you can have even a different scale. This is true in many networks. I mean, even if we are considering, for instance, the network of banks or companies, inside this company there are different structures. Or talking about the example that Maxi was saying before about how the influence and the other things are propagating. We have essentially a network that is connecting by essentially other connections, for instance, different cities. But inside each city there is another network of social relations in which the virus is actually propagating. So usually you have these different networks at different scales. But we are going to focus only on one of those in here. This is a kind of zoom of the other example I was talking about before. So before you saw the picture of the web pages, so web pages and hyperlinks between them. Here I have done a zoom, and not only that, I have also added this part here. Actually, this is the color code for all these things that you are seeing there. So as you see, the web pages are divided in domains, and in this case, they are even divided by the last part of the domain, which essentially refers to the country. No? So what you have here is that even in this huge thing, there is an order. I mean, the order is coming from the domain of those web pages. And that starts to establish some kind of grouping between the nodes. You will see that actually, I mean, this case is not really like that, but there is a relation between those domains and what may be happening behind the process that generated the network. And this is probably the best or classical example for this kind of thing. As I was telling you before, this is a social network, so every node is a person. And this is a classic because it comes from a social study of this researcher in American University, that he doesn't want to say which one it was, but he was both in jail, just in case. And this happened, this was some extra school activity, let's say. No? So it was a karate club. This is why this network is called karate club. Second karate club. So what was happening is that each connection represents interaction outside the karate lessons. And this was taken for a full year. And what happened during that year is that there was a discussion in the club. You have the director of the activity that wanted to keep the rates that they were getting for the classes constant, and the main professor or teacher in the karate lessons, that is this guy here. The director is the 34, I think. That actually wanted to increase the rates that he was getting for the fees that he was getting for the classes. So they started a discussion, and at a certain point the full group split it. It split it following the red and blue lines. And as you see, I mean, there are some relation about what happened in the splitting process and the kind of relations that these people have outside the relation. So the kind of social interactions that they were having. And that leads us to think that actually finding these kind of groups is an important question, because actually they can be related by homophilia or by some other mechanisms that are subjacent to the structure of the network. So this has started a lot of work in first defining and then finding communities. So the definition is essentially, I see. So this is the definition, the kind of very basic definition. So communities are a group of nodes that have more links inside than outside. But of course, I mean, this is not very easy. At first, you need the graph to be sparse to really define that, because if you have someone that is connected to everyone, it makes no sense to actually define this. The second thing is that the kind of groups that you can define is kind of loosey. In this case, it's very easy because, of course, there are very few, but you can have some other configurations of the groups, and this inside and inside will be a kind of, let's say, not very clear definition. But still, this is the only one, or the most important one that has been there for a while. This was associated to this idea of hierarchy. You know? So, essentially, you could have the nodes down here, and they are more related to each other, and they form some groups. But these groups can be one inside the other and make like one of these Russian dolls. Matryoshka, I think they are called, that you start to open and see more and more and more. So this would be the idea also for this kind of group. So you can have a group here, and then this form another group at this level with the other guy, and so on, and they can just merge in bigger and bigger groups. This is a relatively old idea. It comes from computer science environments. So many people was looking for this kind of dendrograms. At the beginning, there are several methods to actually try to find them. And this is essentially the problem here. No? So you have a network, and you have to split it. So you have to find methods that actually split it, trying to, let's say, optimize the kind of quantity that you are searching for. In this case, it would be the ratio between inside and outside links in the connections. There are several methods. I just listed a few of them, but there are many more. Like, for instance, one of the important things about this kind of clusters is that they actually control how the dynamic of how the dynamic of some processes that are on top of the network will behave. You know? So essentially, the dynamical process, like for instance, the POTS model here, or the oscillator synchronization. If you consider that in each node of the network you have a spin here with different colors, or you have an oscillator, and the way in which the full network will synchronize. This is the plots that I am getting here from the work of Alex Arenas. Will depend on this structure of the network. Actually, what Alex found, Alex Arenas, is that the synchronization, this is the number of independent components, start with every node independent, then it falls, and there was a benchmark that they generated with the sensitivity levels. So the first level corresponds to the first unit of communities, the second one to the second level that was in a hierarchical structure, so it comprehended some of the previous networks and so on. So actually, with this kind of things, you could actually check where the structure.
So the oscillators which are synchronized at a given time.
Yeah. So they measure the difference in phase between the different oscillators, and they have defined the number of components. So the different phases that you have is the different oscillators. So the different components. The POTS model is very similar. You just look at the number of colors, and the thing evolves in time. Then there are some more elaborated things like this idea of click percolation, but this works only for very few type of networks. So you have really strong structures connected with one another. That's happened, for instance, in scientific collaboration. Essentially, you do a paper with someone, all the authors from a very connected structure, and then you can just try to find the percolation of this kind of structures. This is another method to find communities. And then the one that is most famous, and probably the one that reactivated a little the field, because this thing started in social sciences in the 70s. Like, for instance, the work of Zachary was already proposing a method to partition the network. Was this work by Mark Newman and Girvan in there was another precedent to this that I will cite later in 2002. But the idea here is that they found a quality measure for the communities. So what you are doing here is you just consider the group and see how many connections there are between the members of the groups. This is this term here, so this is this part of the equation. The second part is a comparison with should be a null model. So you say, okay, let's imagine that the connections in the network are completely random. So that means that for a connection to exist between the node I and j, you are just given a probability of ki over 2m, which is the total number of links in the network, multiplied by ki over 2m, the other 2m is here. And if they are completely at random, if what is happening inside is the same as what should be happening in a random network, I should get a 0. Otherwise, there could be a negative tendency, so a negative modularity, even though that's hard to find, or it could be a positive measure. And what we will try to get is the highest value possible to actually split the graph. So this is the method called maximum modularity. And I will talk to most of these things later, so I will use mostly this new model idea to define the statistical significance. So essentially this is the clustering method that I was explaining to you. The idea is to maximize this. And this is a hard problem because you can choose essentially many combinations of nodes that could actually get a different value of this Q. You should test most of them, or at least find a fast method to actually optimize the quantity. And there have been many attempts. So greedy algorithms, simulating many stem optimization, and many other optimization methods applied to try to get the maximum of this quantity. Still, it has a problem. This was noticed by Santo and Mark Barthelemy. The problem is that actually reach a certain scale is not able to distinguish. No? The scale is given by the square root of the number of links, even if probably you cannot read it. Below that scale, so if you have a group of nodes smaller than that square root, you cannot say if actually the structure is like this, or it will be a good community, or it's split in smaller units. That has to do with the fact that the modularity is a global measure, so it's trying to act in the whole system. Many people have proposed that.
I have a question. So if the modularity Q is larger than 0, it means that there are communities. Okay?
Yes, that's the idea.
The problem is that you don't know, you can't distinguish the communities in the network. Can we?
Distinguish in which sense?
You can find the communities. You can say there are communities, but
no, because to obtain the modularity, you have to say which are the groups. And so this thing of having the link inside or outside, it means that you have to establish the groups before. Then you get every time that you establish a partition, so a certain grouping of the nodes, you extract a modularity value. But that's strictly associated to the partition that you have found.
So you need to have some information about the network first, in terms of doing this.
Yes. Or try every possible combination that, computation is horrible. Or find some other methods like simulated annealing or anything that is trying to follow the directions in which the modularity is maximized. So it's an optimization problem to that extent. And the problem with all this is that, we have modularity, we have all the other methods, and how the people have faced this problem? Well, since you cannot go directly to a real network and say, okay, I apply this thing, I get this partition, and I like it because it's what the modularity says. And some people do that, which is not very good. The general practice has been to choose benchmarks. So essentially, in networks, you know how they have been doing. These have been constructed. You know that there are some community structure, and then you apply your method, and you see if the method is good or bad to actually find what you put inside. This is, for instance, an example. This comes from one of my previous works, and in which I was trying to find which was the importance of each of these nodes for the community thing. So this is what you have different symbols and different, but essentially the colors and the structure is the same. So what you are doing here is you have these 4 groups, 32 nodes in each of them. This is called the global Newman benchmark. And there is a certain KI, which I think is 16 in the beginning. And then you change this K out, so how many connections you have outside. And the original method was to rewire. So you take a link from here and you send it aside. So you can change K out. And here I was doing a different thing, just because of, let's say, practical purposes. I was increasing the number of links. But the idea is that all these methods, you all have a curve like this, essentially. So as you increase the K out, at a certain point, the whole thing will become random. and then you will not see, your method should not be detecting anything else. This is the way in which most of the methods have been tested. Then recently, some people actually started to say that this was not a good benchmark because it has a very, very particular symmetries, which essentially means that you have 4 groups essentially identical, and you are testing your method that should be able to find all sorts of communities of all sizes, of all types on that benchmark that have 4 identical communities, which is not a very good idea. So this was proposed, and I don't know how you can see this. No, it's not very good. So this other method that is essentially other benchmark that is essentially based on the same idea of having communities that are planted. So you essentially are putting there what you want your method to detect. And that have into account that the communities can have, I don't know, for instance, in this case, a power law distributed size. And then, of course, also this implies also a power law distributed degree, because the connections inside are more dense in those that are bigger in this benchmark. But again, the general idea is the same. You just take your method, you apply it to this thing, you change the parameters that control the disorder, and at a certain point, you follow your method until it's not able to detect anything. And you can say, okay, this was the threshold for randomness in the network, or, since you know that theoretically, if your method tested 2 files before, you can see that your method was not so good. No? And this is what has been the cornerstone for most of these methods. So the way to proceed, you do all these steps, and at the end you get a good or bad method depending on how it performs on the benchmark. But this it has a problem, and it's that it's wrong. That's not the way to go. And that's not the way because in general cases you don't have that information about what is happening in the network. So you should not be comparing with what happened in a benchmark where you have put everything inside. And I will explain it later this a little better. So, and this is where we enter in the statistical significance. So this is our work from now on. This is the first example. So this is a very simple graph that we generated. Then we ran the maximum modularity, and we got this value. So, and this partition too. So probably with nice eyes you can say, okay, well, some groups seem to have more connections than others. That's good. And the value of the modularity is not 0. Actually, this is not small for what the modularity usually is. So you would say, okay, there is some community structure. The problem is that this graph is random. It was completely generated completely at random. So it's one of these read model graphs where you just have a degree for its nodes, and then just make the links at random between the nodes. The problem is that this is a small structure, and as like many of the real networks, that implies some fluctuations, and you can have some areas that has higher density of internal links that external just because of the randomness. Still, your method is saying, but these are good groups, and actually they are not. So that's the start of our work. We want to show that actually you should compare with the best outcome from a random graph, not with any outcome. Any kind of mean average outcome from a random graph. No? So this is what essentially led us to define these kind of things, and the main question is this. So if the clustering method, so this was modularity, but the other methods are finding the same kind of structures on that network. I find in groups, even in random graphs, which is the value of those that they find in real networks. And that's quite a scary point because...
Why would not be a community in a random graph? You make something at random, then by randomness.
Yeah, but then you can have fluctuations. So essentially, there can be.
You have other communities which are in this graph.
Yeah.
That's random. And then you have communities.
Yes, but the network was completely generated completely at random. So which is the value of those communities? When you really want to see something that, let's say, introduce more links than a random situation. Because most of these algorithms, what is trying to detect is the communities in the sense that communities are something important for the network that you have at hand, saying that there is a tendency of the nodes to connect more between themselves than with the outside, with the rest of the world. The point is that...
they do, this graph, by randomness, they have more connection inside and outside.
Yeah, but that's the point, no? When you are going to say to a real graph, okay, I have this community here, Is that community something that was generated by randomness, or is something that it was really there generated by a process? I don't know, like for instance in social networks, you can say that people like each other more than, I mean, they try to interact with people that they like, or the other way around. So this idea of homophilia. So which is the, let's say, the threshold of comparison? So is it just the existence of this kind of aggregation, or is it more important to see, to set the, let's say, the threshold in what happens in a random graph? So this is essentially what I was telling you. So there is the two important parts here. One is the null models. Taking a random graph, that is equivalent to the thing that you have. Essentially, that needs to keep at least the degree. And then you can go further and try to keep more properties of the graph. But the degree is, let's say, the minimum that you can actually expect if you want to have a null model for a certain graph. Then the other thing is what we want to compare with, which is essentially what we were discussing. So you probably want to compare not with a completely random graph, or what will happen in a completely random situation, but with the best outcome on a random graph. And say, okay, I want my communities to be significant, they have to be better than that at least. No? So that will be marking the smallest quality that you can consider as good communities. And so this is essentially what I was telling you, that's our approach in this work. We will try to obtain analytically, as far as we can go, some expressions for this best outcome on random graphs, and that will be our threshold of significance. Since what we will do will be statistics, that will allow us to actually define levels of significance like 5% and so on.
I don't understand. You can imagine a situation with whatever type of communities that you want that seem to be very well defined. This is something that can happen in a random network.
Yes, yeah, I mean, but that's the thing, how often it happens. So that will give you the statistical significance of those communities.
Okay, so when you, in previous transparency, talked about that?
Let's go back. Yes.
The best part of a random graph.
Well,
there is the probability that it happens in a random graph.
Yeah, this is why we started to talk about significance and statistical significance on this. So the thing is that the random graphs include all the graphs that have the same degree distribution. So that means also the network that you have, whatever the network is. But the question is how often this comes out there, and that will give you the statistical if you want to evaluate the communities. So this starts with something like this. I mean, actually, we're trying to evaluate given communities, not to find communities, at least not yet. Probably in the future world we will try to do that too. So we assume that the group is given, so we are not going to touch it, we don't want to move anything. That groups, you have applied some method or you have some inspiration and you decide that that's the group you want to evaluate. So the links inside are not going to be changed. And then of course there is the group, the links outside of the community, and I don't know if this is here a node, in particular node I. And then you have all the other nodes that are outside of your community. And what you want to evaluate is which is the probability for this guy to connect inside the community. So which is the probability that this node with degree ki will have k in connections inside. And this is something that you can approximate, because this is not the exact formula. Essentially because this means that you could connect two times to the same node. This given by this hypergeometric function. This is the approximate function that works well as long as there is no nodes with a huge number of connections. But since most of the cases this is not the case, we will go on by this approximation. Otherwise, analytically it's very hard to write the expression. And once you can evaluate this, you can say, okay, let's test it with some random graphs and see what comes out. And this is what you see here. I will explain you later the main plot. So the insets are points. I mean, the points are simulations for a random graph, randomly chosen nodes, and then this might make your group C. and you try to see if the other nodes of the network are following this distribution of kappa Ki, so of the number of connections they have to that group. And so that's the hypergeometric that I go to before. And this is the result. So for randomly chosen nodes, it works. The problem is that it doesn't, when you are not considering them as randomly chosen nodes, when you apply a method of clustering finding, I mean, you're trying to find clusters like maximum moderated on the network, the groups that come out are very connected among themselves. And that gives you these points here. This is, again, a numerical simulation. And then, I mean, with much less statistics, but it goes down like this. You know? So, essentially, what is happening here, the blue curves, is just to help to remember what happens when you are selecting in a random. What is happening is that these are, of course, the Ki of the nodes outside of the group. Remember, because the ones inside of the group are very hard to evaluate due to the correlations. But for those that are outside, if you are in a random graph, you should assume that still the thing of independence that we are, I mean, the assumption of independence that we are doing is working. And the problem here is that you see, I mean, there is a lack of points on this side. Actually, it's fallen down like this. So essentially, those that have more connections with the group are inside the group, so I'm not outside. So you are missing this part here. So and then you have some also some lower part. So the idea is to try to check if we can find this red curve, and the answer is yes. But then you have to take into account something in the full game. So you have again the same picture as before. You will see it several times here. So you have the nodes outside you want to evaluate. You have the group, and then you have the node. I mean, just for simplicity, let's assume that all of them have the same number of connections. So the one that is the worst is the one that has less connections inside. No? So this marks as a kind of threshold. If you have applied the clustering method, you assume that, I mean, what you are expecting that is that most of the connections, the connections of the members of the group are mostly inside, or as much inside as possible. It doesn't mean that it has to be inside, but let's say the Ki maximum that you can get for the nodes outside is fixed by this guy, which is the worst. No? So this is essentially marking you some kind of maximum threshold for the distribution of the Ki of the nodes outside of the community. And this is given by this kind of approximation, which is another hypergeometric in which we are having into account that there is a maximum for the Ki of these guys outside that is given by the degree of this node. You do that, and then you do the numerical estimation as before. This is the same curve as I showed you before. You get this red curve. That is, I mean, it's still not perfect because we are, as I told you before, we are doing some approximations. But it's much better than the red one, and it's going in a good direction actually. So that leads us to the next step, and it's essentially the most important because this will define what our method. So you can say, okay, let's say the worst node inside is then what marks the border between inside and outside. So each degree is the best that the guys outside can do. But this is, I mean, what we're interested in is to obtain this kind of value in a random graph. So this was the idea of later comparing what we get in the given network with this kind of, let's say, baseline. So since this is random, we will assume that there is actually not a hard, let's say, transition between what is inside and outside. I mean, of course, our clustering method will find the best, we'll do the best it can, and we'll take the ones with the highest Ki. But then the guys outside cannot be so extremely bad. So they have to be a kind of soft transition. And this is an assumption, I have to admit, but the thing works relatively well, because this essentially allows us to use string statistics to define which will be the Ki of this guy, or the one that is the best outside. Okay, so based on the Ki of this guy, we will be able to estimate the best outside. Or if we move the game one more, essentially the W minus 1, which would be the second worst inside, will define the distribution of the worst node inside. And this is what is done here. I mean, this is essentially the starting point for a Campbell distribution. So just try to choose which is the best, or the probability that the best is a certain value, less than a certain value. And I mean, once you have this cumulative distribution, you can obtain the usual distribution for k worst. And this is essentially which all the method is based. We tested it in real graphs, but then you have to fix things like the number of connections outside and so on, because the group is here and it's supposed to be given. So you don't obtain so many points to test, but at least the blue curves are the prediction of this process, and the black ones are the numerical thing. And the range is well obtained, and the values are very slightly low or higher. So for all the approximations we have been doing, that's not a bad thing. Then we applied again to the. Well, the first thing is to define the C-score. So this is what will define the scores. Then okay, you have this P of K worst. So you are trying to you have obtained an expression for the probability of having a certain number of internal connections for the worst node in the community. And you can say, okay, let's assign a certain probability to that community, which would be the probability that that you get a value bigger or equal to that worst thing on a random graph. So essentially, what happens is that if you have a real structure, let's say a good network, the communities will be much more isolated from the rest of the graph that they will be in a completely random situation. And that means that the probability, you will have a k worst, whose values is so high that actually this probability will be very low. And this is the probability we are trying to measure. So this goes in the direction that Raul was saying. So what you are trying to know is, I mean, of course, all the networks will be there. The one that you have will be a part of the random sample. But you want to know which is the probability of something like that to happen. And if it's low, that means that you have a good community. And this is how they define this C-score, which is essentially kind of a score of the quality of the community. We applied it to the benchmarks to see what was happening, and we found these are the red points. So essentially, the things start to go wrong before you reach the completely random situation in the benchmark. And wrong means here that essentially you are able to reproduce those kinds of structures on random graphs. It doesn't mean that actually the benchmarks are not good. In the benchmarks, you know what you have put. But the problem is that once you reach a certain level of randomness or disorder in the benchmark, you are getting closer and closer and closer to what you will get in a completely random graph. And then at a certain point, you probably you're not able to distinguish with certain level of confidence between those structures and those that you will get frequently in a random graph. So you cannot say that those are good, in this sense, communities. We did it for the two benchmarks, so the homogeneous and the heterogeneous one. Then the nice thing about this is that it actually, this C-score is based on the worst node in the community. But you can say, okay, I measure the C-score of the full community based on this guy. It gives me a high value, so that means a high probability that this is equivalent to what you find in a random graph. I throw it away. I go for the nest in the land. And I can explore the whole thing like that. So I'm entering higher and higher inside the community until the C goes down. And that will mark the point where I'm actually finding a nice group or a nice score in the community. And this is what we are doing here. So you can stop whenever you want. So this is how you can establish a level of significativity for this thing. And we were interested in what was happening with this kind of method. We applied to random graph first. A community got from a clustering method on a random graph, and we're seeing that this was all the time flat, with small fluctuations here, but never going below, not very, usually going below 1%. And then the thing is that when you do it with a cluster that is good, and you have put it there, plus some random nodes that you are connecting outside at random, you will find this kind of thing. You know? So, I mean, you have, let's say, a big network, completely random, except for a good community that you have put there with a k much higher than that should be normal. And then you have, say, my community is this good group, plus some nodes that I got at random from the rest of the network. This is the way that we play this game. And what the C-score will tell you is, okay, I mean, those nodes that we put at random are the worst in the community. So I will start to take one by one away. The C will be close to 1 all the time until just you find the core that you put in the was good. So then it indicates it goes down for a long thing, and then since there is nothing more, you start to increase again. And then the same here. I mean, we did the same experiment, but this time there were two clusters. So there were two clusters with some random connections between them, plus a kind of sea of big network completely random. We consider these two clusters as the good one. The cluster formed by the two as a good one, and try to ask the method what was happening. And it was finding that actually the two, since the two were good, the two connected was still a good thing. Then you start to take away nodes of one of the clusters until you reach a kind of situation where there is a cluster left plus the remains of the other that are not good for him. So essentially this is very high. And then when you find the second cluster, this goes down again. So essentially it matches where you have detected this. We were just doing this in a completely deterministic way. So saying we take the worst and throw it away. Of course, there are many ways to do it. And this, I mean, if you want to apply this structure detection method, you have to check all the possible ways. But this is not what we were intending. We were just trying to see if it was able to detect something inside. So just use this kind of very, very simplistic approach. And the last problem about the C-score, and this is something that some people have already criticized us, is that we were estimating the full community based on the worst node. And they were telling, okay, but I mean, you are too strict. Of course, the answer is yes, but I mean, you can throw away those that you don't like and then try to see what you find inside. But still, you are evaluating the full thing based on one node. So we try to test another different idea. This is the B score. B comes from border. And what we're doing here is actually created a border of nodes that are bad, let's say. So we classify them as usual, try to extract those that are bad. And then what we are evaluating is not a single node, but the sum of what this kind of probabilities will be in a set of them. I mean, to say it exactly, I should have put the big formulas, but that's... and then what happened is that you get a, let's say, community evaluation. Again, you have to assume that those are the best, that the nodes outside, so the random nodes are let's say, the connections that they have within the community will be given by the best of those inside. But you are not doing any more esteem statistics because you have not a single node, you have a group of them. You know? So you have to use other statistics to apply possibly this kind of thing. And then you get these blue curves. It says that this is less conservative. This is going a little farther away, and this can be displayed. I don't know if you will remember what happens in the Zachary graph at the very beginning. So what may be happening in this network is that you may have a good group that is given by a set of let's say weak nodes that are connected into it. So the whole set can tell you that the group is still good. But if you are considering one by one, those nodes are not good because they have very few connections inside. The thing is that when you have a full thing of those, the combined actions will tell you yes. I mean, this is to some extent significant, and this is why the B score is less conservative. But still, I mean, the randomness of this thing is around 10 in the benchmark. Or let's say the theoretical randomness is 12, but since this is a very small system, most of the people assume 10 as the limit, and this is going up higher before that. So it means that essentially the benchmark started to be weak at those points, even with the B score. And finally, we apply all this to empirical networks and see what happens with the classical communities that were found there. So this is an next example because I put it because I have this nice plot. So the idea is, for instance, this is I didn't add the reference. This is Alex Arenas, C. elegans. This is one of these biological networks. I think it's between neurons. I don't remember now the name for this thing. So this was done by Alex Arenas, and they found this series of groups with different clustering methods. So the idea was to evaluate them, and we applied the same techniques for clustering. Extracted one of these groups. This is, for instance, this is one of them. We were evaluating all of them with different methods. Here I have just an example to show what happens with the Q-core when you try to find, let's say, the core of the community. The networks, I mean, the nodes in reds correspond to this path. So the core methods essentially throw in a way saying, this is not good, this is not good, this is not good, and so on, until you get the C-score falling down. And this is some big oscillations after that. So the green part corresponds to this green points here. This go on, still farther away. And the last thing is this table. I mean, for instance, this is the karate club. As I was telling you, the D-score is based on the combined action of the watch nodes inside this community. So it's in this case it's very important because actually this network is based. These groups are based on that. And as you see, the difference is high for, I mean, the evaluation in one single node, that means that this is completely random. But for the B-score, it's giving you a good thing, and actually the core of the B is relatively high. The things improve if you consider the original karate club. It's a weighted network, where the connections are bigger numbers based on the number of hours that these guys stay together outside the club. And then you see that the things go down. So essentially the connections still, so the strength of the connections reinforce the actual community structure in the graph. We check, I don't know if this is the dolphins, this is the Luso dolphins networks, which was something similar to the karate club, but with dolphins. There was also a split in a group. And the results with the dolphins actually in this sense is similar. So the C-score is not, it's giving you something that says, okay, this is not very significant and it's based on the wash nodes. The B-score is improving and it's giving you much more, a much lower level, so a better level for the communities. And then the college football. These are only some examples. I mean, and you see that here there are some communities that were really bad. But this is what is well bad. In this sense, not that they could be similar to random communities with high probability. And we did much more. I mean, this is just a few of them. We did much more real networks. So, I mean, I hope that to have convinced you of this, these are the messages to take home. Essentially, so that the benchmark are not the ultimate word on distinct clusters, because you know what you put inside, and then the thresholds are kind of quick in there. So it's important to actually evaluate this kind of ideas, so which is the significance of the communities, when you apply the method 2 or random graph. And try to evaluate how often the things that you are finding in the real graphs are found in this kind of random structures. And well, we offer a sound with some approximations way to evaluate these numbers, which are this C and the score, and it has some nice, let's say, possibilities, like this idea of exploring what is inside the community. And well, that's it. The work is this one, and well, I have to change this. This is not it's still 9 something. This one is okay, sorry, but you can find it in archive. Well, thank you very much.
Thank you, Jose. I don't know if there are comments or questions.
So, in the case of the college football, so what is the typical size of the network?
The college, which is the size?
The number of individuals.
The number of divisions.
The number of
nodes.
Individuals.
Well, no, because these are teams. that play together.
And always a team.
Yes, with the different. So this is the football team of the American colleges. This was done by Newman. There was a reference here. This comes from the paper, and these are the sizes of the groups. So I think at the end there was
Okay, but just
around 100.
So I see that they're very small. So around 10 more or less.
The groups, yes. This is with maximum modularity. Also because you have the different confederations. I mean, there are like 4 or 5 big groups, and then they are split in a smaller.
The point I want to make is, so if you have a small network, then it's easy to see just by looking at the network whether there are communities or not. Okay. So, I guess your method will apply when you have really complex network, in the sense that you have many nodes.
Yeah, you can. That's the other thing. You can apply it very big.
Then the point, if the system is very large, then the fluctuations are small. Then these things about random fluctuations doesn't happen very often.
Well, not necessarily. I mean, the system can be big. The communities not necessarily are big. Most of the clustering methods that have been applied to very big databases, like the Notre Dame web pages, trying to find the contents and which are the groups, give you a overall distribution of the size of those communities. So there are many that are small, and then some that can be very big. For the very big, I agree. There can be an easy way to actually check them. For the small ones, you will have to do the same problem.
What would be the equivalent to such an index for bimodal networks?
Bimodal?
We work on plant animal interactions, and
yes.
For us, a community.
So you're interested more in the football. Actually, this reference here is trying to work on that direction, but it's not this method. It's a very different one. The idea I was talking to Andrea and Filippo. The idea would be that if you have a bipartite structure, so members of one community try to connect more with the others than usual, you will have to do the opposite stream. And so, if for instance for the C-score you are doing the maximum, you should apply the minimum for being in the same group. The problem with that is that when you have more than 2, it gets hard because you can have interactions that try to maximize the internal degree, minimize it, or nothing. You can completely random situations, and then you have to evaluate each of them. So that's very tough in this kind of approach.
So if I understand well, we are looking for modularity, and we compare our modularity index with modularity contained by 1,000 randomizations. So that's not correct, according to you, right? We need to.
You have to actually apply the same method to that 1,000 randomized versions of the network, and try to see which kind of structures you get, and compare those with the ones that you are getting in the original network. That would be the way that we do it. But I mean, I don't know if your method is trying to maximize or minimize the internal connections. That's the other.
The software by Roger Guimera.
Okay. No, then I don't know. Yes, that can be.
I don't think it looks for the.
Perhaps we can discuss that.
Yes, it's better.
You have mentioned on the regarding detection of communities, you've centered in node detection, right? So you have partitions of nodes, and there are some works recently about the partitions of communities using links instead of nodes, like one work by Labiot and that. I don't know if you know about it, but I was wondering if you have think of similar method or similar method that you want to implement.
Trying to do the partition based on the links.
The links instead. Sometimes you have nodes that you have to decide to which community to belong. Sometimes it's just a node, it's an interface, right? And it's just
there is similar works also by David Federer and and so on. So it's based on the idea that you have bridges, and even the Gilman Newman first paper is based on that also. You have flows between communities, the same way that you have some kind of information flow. And then what happens with those kind of bridges is that you will have connections that are supporting a very huge flow, because if every node wants to communicate with every other one, then almost any information has to go through there. You have two clusters and any connection. That's the classical example. So what Newman was doing in that way was just cutting that link. Then you have some other approaches. I don't know exactly that one of them yet, so I don't actually thank you can pass on the reference. But the other one by Feller, what they do is actually with these nodes, if you are considering nodes or links, it's very hard to decide in which community they are. So they measure kind of instability for the classification. And they say that those that are more unstable are those that has to be out.
Okay, Emilio.
Is your analysis giving any insight on which method to detect communities is better?
We haven't tried that. No, we haven't tried that. We could do a competition. To see which is the best method. Actually, Andrea and Santo, I think, working with the benchmark, we're working in this kind of idea of trying to see which methods are better in detecting communities. But those are planted communities, which is a kind of tricky thing. We could compare the two of them, but the problem is that if you do it on the benchmark, you will have this question that for us, the communities on the benchmark have to be dubious before that the benchmark is completely wrong.
What is the final goal of recognizing communities in network of population?
The final goal is that actually these nodes should have some kind of thing in common. Like for instance, the famous question of the web pages. If you are considering how the web pages connect, you are expecting that those that treat the same topic should be connected together in one cluster. Because when you write, I don't know, Wikipedia, you write some description or something, you usually tend to connect to those pages that are simple. So, but that's just one example. In the social things, the social sciences, the idea is that those groups are groups of friends or group of people that interact more than just, or that they have some internal property that makes them more equal than the others. And that's the kind of things that you are trying to infer with these clustering detections.
If I can add, it was a nice example of the email network in the University of Tarragona, when they tried to detect communities. What came out was very clear, which is that administrative organization of the university is different from the real communities which are in the university. So you can organize something administrative in departments or whatever, then you try to really identify which are the communities, and that you see that you should be organizing the thing in a completely different way. And then there is the community of the administrator, which has nothing to do with it. More questions or comments? Well, if not, as I said, he will be here today and tomorrow if anyone wants to talk to him.